Today we're going to talk about crash consistent agent execution in Agentic AI. Before we talk about this, LLMs are getting better, agents are getting better. The way they execute, the way they hold memory, handle multiple tasks, and then we are almost there where we are at multi-agent orchestrations, where we are almost giving it pretty much most of the reasoning calls to take, unless and until there is a very specific workflow use case where it has to have a human in loop. So they are autonomous to some extent. Let's say you're building a system, a ticket management system, and an autonomous agent basically handles cancellations and refunds. Let's just talk about one facet of it where it has to handle a cancellation and a refund, right? So let's say a customer says my order never arrived, right? Go ahead and cancel it and then refund. So the agent is now supposed to respond and then follow the next set of steps to go ahead and carry out this task. So I'm going to have a very simple 6-step workflow on how to execute this, right? So the first thing, you need to know which order it is. You pick up the order, you check the refund policy. There might be multiple use cases of where you will or will not give a refund. You check the policy and let us say it is true that you can refund. And then you go ahead and cancel the shipment because that is what they had asked. So you go ahead and cancel it and then you issue the refund, right? And then once that is done, you have to send out a confirmation email and then you close the ticket. So this is a very simple workflow. So let's say that it issued the refund in one of the use cases, and let's say the pod failed or terminated, right? So there are 6 steps. It performed 4. It issued the refund. Now there are 2 steps remaining, and the pod failed. And then the pod comes back up, right? And then as soon as it comes up, it checks what is the last state. It says that step 3 is completed, right? And it just basically picks up step 4. It goes ahead and then it issues the refund again, and then it sends the email and then it closes the ticket. Now the thing that happened here is because the pod failed during step 4, so you basically refunded it twice. So the format of this execution is a distributed transaction. Basically, a transaction is whenever it has to complete pretty much it has to execute all of the tasks. That is when it completes. A distributed transaction is when it is doing this in multiple locations. So let us say, for example, you have to record a payment or it has to go through, right? And if there's a transaction, let us say you have to do it in Stripe, or let us say you have to do it in Zendesk, and you have to do all of this in parallel, right? That is what a distributed transaction is. And one variable that changes here is that one of the component here is non-deterministic. What it means is that deterministic is every time you replay something, you get the same result. Non-deterministic is every time you do the replay something, you get a slightly different or maybe completely different. But there is variance. So that is what non-deterministic is. And here in this distributed transaction, the non-deterministic part here is the agent, right? You have to execute it. Let us say if a human was supposed to do it, they will basically do each step individually. They'll verify, they'll check, and they'll do it, right? And if you ask them to do it again, or if you would check the database again, it'll show pretty much the same thing. It'll replay the same thing. But an agent will not do the same thing, right? So what happens here is the agent is probabilistic, right? It doesn't directly go into refund because it's given a bunch of tools to handle, and it just calls one of them. So here it can either pick store credit, or it can escalate to a human, or it has to issue a refund. So there is a 61% probability that it picks issue refund. The next time you run it, it might not pick the same thing because it's probabilistic, right? So that is why it is non-deterministic. So the first thing that we want to kind of do here, we want to differentiate each one of those steps. All those steps do not carry the same weightage. Reading from a file and refunding an amount is not the same thing, right? So we want to kind of categorize them, and we want to put it under pure, idempotent, compensable, and then irreversible, right? And if you were to kind of dive deep into each one of them, pure is basically just reading a file. There is absolutely no damage in doing that. And even if you do it 100 times, that's not going to cause any kind of an issue. And when you're doing anything that is idempotent, it is already handling the use case where you only do it once, right? And then compensable is whenever you can go back and change a status, or even you can undo something. That is what a compensable task is. Irreversible is mostly one-door decisions. Whenever you do something, you cannot basically undo it, right? So these are the categories or classes we want to put each one of those statuses in. So this way, we are adding weightage in terms of importance on which should be handled with caution, and which ones might, even though you might run it multiple times, it might not really be a big thing. Now, the way you kind of solve this is, first thing you want to do is that you want to quarantine everything that is deterministic. We spoke about deterministic and non-deterministic. So anything that is, whenever you replay it, it will give you the same result, that is deterministic. So we want to kind of quarantine everything that isn't deterministic. Anything that is basically agent, tool calling, LLMs, and so on and so forth. So the first step in doing this is that we want to have a journal. We have a checkpoint that Landgraf and others use. What it basically does is that, and a simple example would be like, it will capture that you need to go, the policy confirms that there is a refund and you can go ahead and refund. That will be step 3. The same thing when you have it in a journal, the way it will record that is, the policy confirms that there is a refund is initiated, refund is completed. So this way there is more granular logging or journaling in terms of what is happening. So this way, whenever we want to troubleshoot, or whenever the agent hangs and whenever it tries to retry the task, this data will help if it went through or not, right? And moreover, you don't want to go ahead and check pretty much all of the each one of the world's data, right? And before anything happens, the first thing you want to do is that you want to append as soon as it happens, before anything downstream even proceeds, right? And whenever it breaks, whenever it hangs, or whenever the pod fails, any of those use cases, it just comes back and then it basically reads the journal and never re-invokes those each one of those functions. So once you implement the journal, it comes back and then it checks basically the journal each time it fails, or whenever it crashes or hangs or freezes, whatever it might be, it comes back and checks the journal, and it'll show that the refund was issued. And it'll not go ahead and issue it again. It'll go ahead and then send an email, and then it closes the ticket, right? So there is one more issue that will occur. The thing here is that if there are two workers, right, and if both of them are on the same trajectory, let me maybe explain this in a bit differently. So let us say there is worker A, and then it goes ahead and executes the task, and then it freezes. It doesn't like slow or stop or anything. It just freezes, and the release time expires, and just worker B takes over, and worker B executes, and now worker A basically starts again, and then did not even know that it was frozen, right? And it also goes ahead and executes the same trajectory, basically the same task. Now what happens here is that both of them are going to execute the same thing, and both of them are going to keep making the journal a mess, right? So the way you kind of handle this here is that you add a fence. Okay, a fence is not added with the worker, it is added with the journal. So an analogy on how to fix this is, you basically give a pass. You give maybe worker A a pass, and let us call that pass as 41. Okay, and then worker A goes ahead, and then it freezes, and then or it stops, and then the lease expires, and it is given to worker B. Now worker B is not given the same pass. That was what we were doing right now. So worker B is given a different pass, but the number is incremented to 42, right? Now what a fence basically does is that whenever it goes ahead and writes in the journal, we ask what is the highest number. So the worker A was 41, and worker B will now give 42, and it will let worker B write in the journal. And once that is done, it will go back whenever worker A unfreezes, and then it starts the task again, and it goes to the journal and it shows 41. It will not let it write in the journal. The reason is because it will only take the highest number. It already has a record of 42, so it will not take 41. So that is one way to use fencing to kind of avoid messy journal writing whenever a worker freezes. Now, this is where you've fixed pretty much some of these failure cases most of the production use case has in enterprise AI. And you want to kind of know, how does this even hold? How are you sure? Right? When you're having a distributed transaction, when it's happening in multiple places, how do you even test this situation? So this is where distributed simulation testing comes in. So what it basically does is, it will simulate each one of those distributed transactions. Whenever you go ahead and execute each one of those steps, you will basically simulate all of those steps externally with a very controlled environment in each one of those outputs, right? Let's say, for example, you're going to make a Stripe refund. And whenever you're doing it in production use case, you just go to Stripe and then you initiate the refund. But in this setup, what we will do is that we will set it up in such a way that we will have two ledgering. One is the journal that we created. That is the one that it will use. And there will be another journal that we are going to have as a shadow ledger. So that is all the simulated ones. We are going to simulate like Stripe. But in Stripe, we are going to capture how many times we got the refund. Even though the agent might not know in its own journal, the shadow journal will indicate that there was two transactions that is being done. So that is basically the setup. So this is the setup. So what you kind of do is that you set up the 5 phases, basically plan, intent, the call, commit, and next. And what you do is that in this simulation, you make sure that there is only one worker node, not multiple that is run in parallel. And you try to fail it in multiple cases. You can change the clock. For example, you can jump the time to 45 seconds. After each worker completes it, between recording and completing it, you can kill it. So you can do multiple things to simulate this, right? And whenever you're trying to do this, this is where you can capture if the journal is working or not, or if there is any issue there or not. Because when you're simulating it, you know in the distributed transaction if each one of those tasks completed or if it kind of did it multiple times, you will be able to do it in the shadow ledger. And if this simulation will help you resolve if there is any kind of multiple irreversible tasks that are being executed. So the way you kind of record this will be like the journal will record as $250 was refunded. But the shadow journal, we will know that in Stripe the refund was twice because we are simulating it, right? And we are capturing the log. And this is how you run tests on agents that kind of have irreversible steps in its process so that it's production grade. And the questions that you kind of need to ask in each one of those steps are: is there anything that is irreversible that happened more than once, right? Was anything that started but never got resolved? Did an abandoned run leave something behind? Basically, were you not able to undo it? Is something missing in the record, right? Or did two workers have were working on the same trajectory? Basically, did the fence even apply work or not, right? And if you do this multiple number of times, 10,000 times, 20,000 times, each one of those red blocks that you see, this is the shadow ledger, which basically says that the payment went twice. And if you're able to monitor this, you will be able to pretty much get to zero violations. So this is how, to some extent, you'll be able to have a crash consistent execution agent.